You'll help. Feel that.
Hey there, everybody. We're going to get underway. Once again, happy to have you with me. A couple of updates on my end. So as I mentioned on Friday, I had my first vaccine shot within that. Went fine, although I'll tell you, it was about midnight Friday night. My arm, so painful. I don't know if you've had a tetanus shot before, that kind of sensation. I was definitely feeling it. A lot of people said, well, it's worse the second day. And I thought, oh, if it's just going to keep getting worse, it's going to really be bad the second day. But that was about my most, my peak pain. After about a day or so, completely fine. So 2 weeks from now, my second one. So that's one piece of good news. Second piece of good news is, as you might recall from first day of class, this last year of pandemic, I've been working on my golf swing. I've been making no progress until today. I think I've come up with something. I think I have corrected my primary flaw that I've had in place for the last decade, 3 decades. So that's win-win. If I can both fix my golf swing and get vaccinated, those are tough to beat. Now, thought about where we're going this evening. So we're going to be looking at ideas here in chapter 9. I know where we're at within the semester, and I know the pacing for how we move along. After we get through the ideas here within chapter 9, the semester is going to feel almost over. We've got almost nothing left after this. I know we've got a chapter 10 on gases, one on intermolecular forces, a little bit on solids, but all of those are a much briefer look. So if you can mentally stay in the game here with the ideas that we have in chapter 9 as we're moving to the next exam, you are doing a great job, okay? It's going to be over really quick after that. So I really need you to try to focus best that you can as we work on here with ideas within chapter 9. Now, if I look at with our attendance, our participation here, this would be the same thing that I see when we would be in in-person class. We're at about the point in the semester where if I looked around, the classroom would just seem a lot emptier than usual, because people, their focus changes in different ways. They prioritize different things. So my message for you is, if you're here right now, if you're here to be learning in the space, let's do our very best to maximize that learning, okay? I want you to do so much better with your learning than the people that aren't even tuning in, okay? So, and that's especially important with these ideas because as you've seen within this, we're not doing calculations and stuff. These are all about applying ideas. So if we can master these, the actual ideas, we're going to do really, really well with this entire set here. So what I'd like you to do initially here, look around your environment that you're in right now. Consider if you have distractions in place. Are you able to really focus with what we're up to? Let me send you a poll on that. What's your setting right now? Do you think you're going to be able to really attend to what we're talking about? My setting, same as ever. I got my dog sleeping here on the carpet, got a pile of chemistry books next to him. My cat, as you know, will probably be making an appearance. So I'm trying to keep things, at least on my end, same kind of zone, so that I can really be trying to attend to our time that we have here together, because I think it's going to be really important. Again, I want to make it so it's worth your time. If you're spending the time within this, let's really try to be engaged so that we can share ideas and do well with them. And it seems like with most folks, it's trending in that particular direction, okay? I see a lot of 4s and 5s within this, so let's see if we can make that work. So our ideas here, last time we introduced our VSEPR theory, valence shell electron pair repulsion theory, with the idea that we'll have different electron domains around a particular atom, and that these electron domains, be they bonding or non-bonding, are going to spread out to take as much room as possible. So when we looked within this video, when we were first exploring the idea, I wanted to illustrate a couple things. I wanted to illustrate what happens when we have, in this case, bonds around a central atom and how they move as far apart from each other as they could. If they were all bonds, we were describing that as being a tetrahedral geometry. When we had four of them present. Within our tetrahedral, we had bond angles of our 109.5. And that would be different if we were to change some of the bonds and put instead lone pairs, which were going to be then non-bonding environments. So that was our introduction that we had last time to VSEPR theory. We had this particular table that I think we were becoming acquainted with, where we said if we could draw the Lewis structure and then apply VSEPR theory, we could begin to understand what the name of the geometry was, estimate the bond angles that were involved, and also determine the polarity of the molecule. That's an idea we're going to get to tonight. We're also going to look at not just when we have 2, 3, or 4 electron domains, but when we go beyond that, when we have 5 or 6. So we're going to have other geometries that we want to become familiar with. Now, when we have 5 or 6 electron domains, if we think back to chapter 8, those were called hypervalent. Hypervalent means we're going beyond an octet. And I know if we have 5 or 6 electron domains, we have to be beyond an octet. And so on the right-hand side, you can see all of these examples on the far right in the small print there, different formulas for molecules that are hypervalent. And so I grabbed a select number of them right here. In each of these cases, we had a central atom of phosphorus, sulfur, xenon. Those are all okay with where we said we had hypervalent. And when I say okay, those are all larger. Those are all from the 3rd row and down. So I'm not going to stress if I violate an octet with those, if they exceed an octet. So when I'm beginning to think about what the Lewis structures would be like, with the phosphorus, I see that it would have a formal charge of 0, and it's exceeding an octet. Sulfur, formal charge of 0, beyond an octet. Same thing with xenon. Now, one thought within here, if I'm trying to write the Lewis structure for these, I think it's pretty easy. All of the ones that I have on the outside here, if it's chlorine or fluorine, I see that they are forming single bonds. And then if I look at the central atom within that, I want to make sure, in order to have a formal charge of 0, that I have the correct number of valence electrons that I'm showing there. And by that, I mean, if I look at phosphorus here, Phosphorus, if I count over for the left from the left, 1, 2, 3, 4, 5 different valence electrons. In the structure, one's in a bond, one's in a bond, one's in a bond, lone pair, that gets me to 5. SF4, I have 1, 2, 3, 4, 5, 6 valence electrons. 1, 2, 3, 4 in bonds, and then 2 more, that gets me to 6. Xenon with 8, 1, 2 in bonds, 3, 4, 5, 6, 7, 8. So for me, these hypervalent ones, I find pretty easy to draw. If I'm going to look at SF6, sulfur again, 6 valence electrons, 1, 2, 3, 4, 5, 6. So I find I can quickly put together these particular Lewis structures. Let me send you a polling question on that. When it comes to doing these hypervalent ones, think about what does it mean to draw these, to make these, compared to when you do the Lewis structures for something that you have not memorized. And by that, I mean, we introduced a process that we could do where we add up the total number of valence electrons, we make a sketch, we complete octets on the outside, we consider then octets for the center, we might have to shift lone pairs, that whole process right there. I want you to compare that versus these hypervalent ones. Do you think these hypervalent ones are easier to draw, about the same, more difficult? They're all easy or they're all difficult? What are your thoughts? As those are coming in, as your responses are coming in for that, a pretty good way to practice this to see, okay, can you draw these correctly? All of the ones where it says example on this, in this image on the far right-hand side, all of those would be ones that would be good practice for drawing Lewis structures. But then here, most folks are saying about the same. I buy that. For me, they're a little bit quicker, but they're about the same. Within each of these, the key thing that we're looking at is we want to know the environment of that central atom. We want to know the electron domain geometry for that central atom and think about then what the molecular geometry would be. That's why we're drawing the Lewis structures initially anyways. We want to know the number of bonds that we have and the number of lone pairs that we have. So let's begin to explore some of these other geometries then. Let me explore this one, okay? And by explore this one, I'm going to make it so we have 5 electron domains. First of all, when we have 3 of them, that was a trigonal planar. 4 of them, it turned it into a tetrahedral. When we have 5 of them, this is our shape. Trigonal bipyramidal, trigonal bipyramids. It's making a 3-sided pyramid that would be on the top and a 3-sided pyramid at the bottom. That's where the trigonal part comes in because we're making it 3-sided, bipyramidal because we have a pyramid that would be pointed up, a pyramid that would be pointed down. This has 5 electron domains. When I look within that one, I notice that some of the angles are 120, 120, 120. That would be the ones here in the center. Some of the angles are 90 degrees, like from the top to the side, from the top to the side, from the bottom to the side. And I guess I also have one of 180 degrees between the top and the bottom. This combination of angles, in some ways, it's more complex than a tetrahedral. There's more going on. One important thing that's going on when we have our trigonal bipyramidal is we have 2 different types of positions there. The ones that are up and down are called the axial positions. And the 3 that are in the same plane are called equatorial. Now, when I say up and down, I mean, you could obviously tumble it around, but this is the picture that I have in my head. I've got this triangle, the trigonal planar portion, and then I have one above it and one below it. So in the trigonal bipyramid, there are 2 axial positions and there are 3 equatorial. That's going to be important for us. So I want you to know the names and be able to think about that. So an initial question for us. when we have these 5 electron domains, meaning it's going to be a trigonal bipyramidal there, where do the lone pairs go? Are the lone pairs, when I substitute those for bonds, are those going to go axial, top and bottom, equatorial, which would be within this triangle plane, or does it not matter? Let's explore it within the sim. So right now they're all bonds. I'm going to remove one of those and put on a lone pair. So let's see if we can make out where that one went. To me, it looks like it went equatorially. Okay, it looks like that one went equatorially as well. It appears in our trigonal bipyramidal structure, the non-bonding electrons, the lone pairs, it looks like we are placing them equatorially. We're not placing them in the axial position. And sure enough, that's going to be the case. If we have lone pairs, when we're placing them within the trigonal bipyramidal one, we're going to put them in the equatorial positions rather than in the axial positions. So I'm curious right here. I want you to predict the geometry for me. If you have 2 bonding domains and 3 sets of lone pairs, I'm curious, can you begin to understand, predict what that structure would look like? And let me ask it this way. Is this something you can visualize? Could you visualize and make a prediction for a VSEPR predicted geometry that has 2 bonding domains and 3 lone pairs? I know it's something that you could perhaps look up on a table, but is it something you can visualize? As I'm thinking about this, I'm going to have 2 sets of bonds, and then in the equatorial position, I'm going to have lone pair, lone pair, lone pair. And that's what I'm trying to visualize. In terms of our results here, pretty much split across the whole board. This is what it's looking like to me. I'm going to have 3 lone pairs within the picture and 2 bonds. So when I place them then equatorial, 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 this ends up being a linear molecule. Now, when you looked at your formula and the number of lone pairs and what was going on, it might not be obvious initially that this would be a linear molecule. But that's what our resulting structure is. This would be the case then where it's shown right here at the bottom. Xenon F2, lone pair, lone pair, lone pair around the central atom. And then the bonds are opposite, being placed in the axial positions. Now, if we move from 5 to 6, then we get to an octahedral one. So let's first think, are we also going to have axial and equatorial positions when we're thinking in an octahedral? So an octahedral, I see trigonal planar, I see tetrahedral, trigonal bipyramidal. This gets me to the octahedral. In the octahedral, I have a lot of angles that are 90 degrees, 90 degrees, 90 degrees. And I can rotate it around different ways. Let's say I grab that top position and I pull it to the side. It looks the same. Let's say I try to keep track of that one again. Let's say I grab and pull it to the bottom. It looks the same. The point I'm trying to make with this is, in an octahedral, we do not have axial and equatorial positions. All of them are equivalent. Okay, the only one where we have these names, axial and equatorial, and we have to think about where things are placed first, that's with our trigonal bipyramidal. With our octahedral, we don't have to worry about that feature. If we're thinking, well, where do the lone pairs go then when we have the octahedral? Let's look at it. So I can initially put one lone pair in 5 bonds. It went in one of the positions. Doesn't matter where it goes, I end up with this being the resulting shape. This is called a square pyramid, a 4-sided pyramid as it's pointed up. If I have 2 sets of lone pairs in 4 bonds, this is called a square planar. All 4 of them are now within the same plane, all 4 of the bonds. The electron domain geometry is octahedral. The lone pairs are being placed above and below, and I have all 4 of the bonds now all in the same plane. This is as far as that we're going to go, okay? As far as what would it mean to have a central atom within our set. Within our octahedral, we had 3 different arrangements there. They could all be bonds where it would be octahedral. We could have 5 bonds and 1 lone pair. That was our square pyramid. Or 4 bonds and 2 sets of lone pairs that made it a square planar. Now, if I look within the set, the strategy for any of these, I would first draw the Lewis structure. I would account for then what the electron domain geometry would be. And then I'd think about what would be the resulting molecular geometry. Within that set, when we ask students questions about these, I know which ones score the lowest. The ones that score the lowest are ones like SF4 or the xenon F4. Because people, if you shortcut it and you say, oh, I got 4 right there, it must be a tetrahedral. These are not tetrahedrals, okay? In both of these cases, they're not tetrahedral because we either have 1 set of lone pairs on the central atom or 2 sets. And I just know that in terms of the process, these are ones that students have more difficulty with because they think, oh, well, it has 4 bonds, it must be tetrahedral. I'm very familiar with that. It all comes down that we have to be careful with what our central atom is. Another feature of that then of our VSEPR predicted geometry is thinking about the polarity of the molecules. Really classic example within this one, if we were to compare something like carbon dioxide and H2O, I would say both of these are going to include polar bonds, but the CO2 is a non-polar molecule. If I looked at Lewis structures for both of these, remember the Lewis structure, it's not telling me the connectivity, not telling me the geometry, it's just showing me how the things are connected. So in CO2, I see double bond, the central atom in H2O, you see single bond, lone pair, lone pair. I say all of these are polar bonds. Let's think back to the, I guess that was in chapter 8, where we're looking at the polarity of bonds. Remember what we did within that. We first thought, okay, let's think about differences in electronegativity. Fluorine was the most electronegative, meaning that when it was in a molecule, the electron density was more around that particular atom. The next tier of the most electronegative were the 2 atoms immediately to the left of it and below. So nitrogen, oxygen, chlorine, bromine, all quite electronegative. And our pattern was, as we moved up and to the right towards fluorine, they were becoming more electronegative. The last thing we wanted to be aware of was, where do we place hydrogen within this? Because hydrogen's a non-metal, even though it's way over here on the left side, hydrogen's electronegativity placed it just to the left of carbon. So I'd say within the set, oxygen is the most electronegative, then carbon, then hydrogen. And when I say amongst these, I was just trying to look at the ones in these 2 molecules. So I'm sure that a bond with carbon and oxygen is going to be polar. It would be a polar covalent bond of some type. It's not ionic, but it would be polar because there's differences in electronegativity. There's also differences in electronegativity between the hydrogen and the oxygen. That's also going to be a polar bond. So I'm first classifying the bonds and considering if they're polar or not. Now, how does CO2 then become nonpolar? Because when we're looking at these, we're thinking about the vector quantity. We're thinking about how you can have a bond dipole pointed from the carbon to the oxygen and from the carbon to the other oxygen. And if they're equal and opposite to each other as vectors, they cancel out. Vectors, I'm accounting for both the magnitude and the direction. So this, even though it has polar bonds, the overall dipole moment is 0. CO2 is a nonpolar molecule that includes polar bonds. How about H2O? Would it be the same thing? So you might look and say, yeah, it should be the same thing. Because look, they're drawn in a straight line, but they're not in a straight line. Remember, it is a bent molecule. The electron domain geometry is tetrahedral, but the molecular geometry is bent. What's making it be bent? It's because I have lone pairs up here on the central atom. If I look within this notation here, I think that the central atom oxygen is partially negative. I think the hydrogen atoms are partially positive. And overall, these do not cancel as vector quantities. Overall, I have a negative region at the oxygen and positive regions at the hydrogen. That's going to be a polar molecule. And you might ask, well, why do we care if things are polar molecules or not? This is going to be a really important skill that we need in chapter 11. As the ideas come together and we begin to look at aspects of intermolecular forces, a really key thing we're going to have to do is determine whether a molecule is polar or not. Within our PhET sim here, I tried to illustrate this a little bit. I tried to first of all say, if we have a two different atoms, if we adjust the electronegativity on those, we could make one side partially negative, one side partially positive. In an extreme case, we have a really clear negative and a really clear positive, and it's approaching an ionic compound. We have a positive side and a negative side, and if you put an electric field, it would align with it. That's what it means to say it has a dipole moment. For this diatomic one, if you were to take it and there is no differences in electronegativity, now it's nonpolar. And it gets a little bit more interesting here when we have a shape that's just not two atoms. So what I was trying to illustrate within this one is you could initially have bond dipoles because there's differences in electronegativity. But there's no molecular dipole because they're set up right now as vector quantities and canceling. If you put an electric field, it's not going to align with it. Now you could change that. You could change it so that the bond dipoles are not equal to each other. That's what that yellow is now trying to illustrate. This would be the dipole moment for the molecule. So one way that you could manipulate it is you could change the magnitude of the bond dipoles, but you can also change the geometry. Notice by changing the geometry, you can affect whether they cancel or not. So I've got, in a cool way, both of those features. I'm thinking about differences in electronegativity, and I'm also thinking about the geometry. So this is a really cool extension for me of how I apply VSEPR theory. So when we're thinking about it, before we were talking about whether a bond dipole was polar or not. Now we're seeing that you could have examples where the entire molecule has a zero dipole moment, it's nonpolar, depending on the symmetry, depending on the shape. So let's step through then and just make sure we're seeing the same thing when it comes to the shapes. So I mentioned before that one thing that would be useful if you have these particular tables and you wanted to consult these, one thing that would be useful would be to consider the corresponding bond angles within them. Is it 120 degrees like in the trigonal planar? Is it 109.5 like in the tetrahedral? I'd add to that, what does it mean to see whether or not they are polar molecules? So the way I'm asking this, which of these are going to be polar molecules with a permanent dipole moment? So what I'm trying to look at these and saying, okay, does the bond dipole cancel or not? I don't think it cancels here in this particular one. It's a bench shape. The bond dipoles do not cancel. In a trigonal planar, they do, if they're equal and opposite, and in a linear one. So this would be one that would lead to a polar molecule. How about this group? See if you can see the shapes here. Being able to visualize it, I think, helps. Look within the shapes. Do you think that you're going to end up with polar molecules here? You will when it's a bent structure. You will when it's a trigonal pyramid, like NH3. In a tetrahedral, they cancel. That one might not be as obvious for you to visualize, but you can trust me on that, okay? In a tetrahedral like this, when you have equal and opposite bond dipoles within the set, it ends up being a nonpolar molecule. Now, what do you think of something like this? CH3Cl. Make a quick sketch of that, okay? Give you a hint, carbon's the central atom. What are your thoughts on that? Is that going to be a polar molecule or a nonpolar molecule? Let me send you that as a polling question. What do you think about this CH3Cl? Polar or nonpolar? So what I'm trying to do here, I'm trying to visualize this as a 3D shape. And I guess in order to do that, I'm first thinking a little bit, well, what would be the Lewis structure? And then what would be then my VSEPR predicted geometry? I think that's what's going on in my head. Then I'm thinking about that almost like a model. And I'm trying to think, would I have the bond dipoles cancel or not? That's what I'm trying to think through within my thought process. That's what I'm trying to work through. Take about 10 more seconds on this. This language of saying it has a permanent dipole moment, that's another way of saying, given that shape, given that geometry, it is a polar molecule. Something that is a polar molecule has a dipole moment greater than 0. A nonpolar molecule is one that has a dipole moment of 0. So when this is saying, what would have a permanent dipole moment? That might be the language you'd see in a question. That's another way of saying, is it a polar molecule? Then this one, we're trending a little bit to say polar versus nonpolar. We're not quite to 50% on that because we have a few other ones within the set. This idea of don't understand the question, what I'm trying to get at would be based on the shape that we have of the resulting molecule, do the bond dipoles cancel like we had in CO2? Or do the bond dipoles not cancel like we had in H2O? If I'm thinking about CH3Cl, I'm thinking that it is a tetrahedral geometry. The carbon atom is bonded to a hydrogen, a hydrogen, a hydrogen, and a chlorine. I think it is a tetrahedral, but I think it is a polar molecule because all of those bonds are not equivalent to each other. There's a hydrogen, and a hydrogen, and then a chlorine. So they're not going to cancel as vector quantities. In order for them to cancel as vector quantities, my point with this is you can't just look and say, aha, it's a tetrahedral. In order for them to cancel, they must be vector quantities that are the same in each of those different directions. Take a second. Tell me if you have a question on this one within the chat. Tell me if you got a question on this part. Okay, a couple of thoughts as far as what's coming in here. Let me put it this way, as I'm seeing different things, different features. The only time they will cancel is when they are all bonded to exactly the same atom in the same way. Soon as I have different ones, then the electronegativities are not the same and they don't cancel the same way. If you make any change within that, it will make it so it is now no longer canceling as vector quantities. Okay? That would be my thought. There's one Riley has here. Would this have a molecular dipole pointed towards the Cl? Yeah, I think my Cl is more electronegative. I think would be pointed that way. CH2, Cl2, I would say that would be, yeah, again, the only time they'll cancel is if they're all identical. Let's look at these geometries. Think about which of these would be polar molecules or not. I think the cases where that they would end up being polar are these two right here. This linear example, if they are the same bonds in each direction, they're going to cancel. This trigonal biparameter one, the way I think about this one is if I have three in the same plane that are equal to each other, they cancel each other. And then above and below, they cancel each other. So this is my way of thinking through the details of saying why that would also be a nonpolar molecule when all of those bonds are the same. One more within the set here, okay? This would be in our last group. See if you can visualize within this one to see if you have any of these that would be polar molecules or not. As I look within this set, I think only this one right here. I think you can have an example where it's a square planar, where they would cancel if they're all the same bonds all the way throughout, as well as what I see with an octahedral there. Okay, now I was stepping through these different parts. Hopefully you can visualize these as a feature, but this is sort of our last part of what we do when we're looking at applying our VSEPR theory, being able to determine if something is a polar molecule or not. This part right here, as we wrap up this first part of the chapter, here's a couple sets of problems that I suggested last time that I don't think we could completely answer because we hadn't started to talk about what happens if I have 5 or 6 electron domains. But I think we can now. So this question 9.23 is looking at that. 9.25 is if I look within that, several of these examples are with hypervalent. So I'm sure that for example, SF4 would be an example we looked at. PF6 anion, that would be another. So these would be ones that are applications of what we were talking about just this evening. These right here, really good applications, predict whether the following molecule is polar or nonpolar. So within these right here, we can't simply look at the formula and say, okay, now I know. What do we want to do? Same plan. Let's start with the Lewis structure. Look at the electron domain geometry. Use that to now draw and think about what the molecular geometry would be. And then finally considering, is that resulting in a polar molecule or not? All of these really good applications. And when I say really good applications, to work through that entire series. So what we have at the start of the chapter is I'm trying to think about exam questions or skills to have. Within this first group, it's really important to be able to draw the Lewis structures, describe the electron and molecular domain geometries, think about what would the ideal bond angles be, and then consider distortions from those. Those are, I think, exam questions from that first part. Within this next part of VSEPR theory, when it comes to polarity, it's what I just mentioned. We want to be able to draw the Lewis structure, determine the VSEPR geometry, and identify whether it's a polar or a nonpolar molecule. Where we're going to take that now is, as we move through the rest of the chapter, we're going to move into this zone right here, where we're going to look at orbital overlap and what's called valence bond theory. Our objective for this, and we're going to get started on it and then pick it up next time, we want to explain how this idea of orbital overlap leads to the formation of covalent bonds. And we're going to apply something called valence bond theory and begin to think about hybridization and how that explains our structure. So I think in for some of you, you've heard this idea of hybridized orbitals before. You might have heard of that in a high school class. You might have heard of it and it went in one ear and you forgot about it. My hunch is some of you have already done something with hybridized orbitals. So what I'd like you to think about within this one is, what prior knowledge do you have on that? Is that something you've worked on or not worked on? And the reason I'm trying to say it that way, think about it that way, I'm really sure that this idea of valence bond theory, which is in 9.5 and 9.6, for almost everybody in the class, you can absolutely get these ideas, but you're probably going to have to see them about 3 times. When we have new ideas in this class, that's oftentimes the case. The first time the information is presented, it's a little bit shaky because it's just too foreign for you, and you're able to take away a few of the ideas for it. You then interact with the idea a second time, and you get a lot more out of it. By the time you interact with it a third time, you can really put all the parts together and master it. So where this idea is going to show up, how you could see it multiple times, we're going to begin this idea tonight, and we'll also talk about it a little bit on Thursday. The pre-class video I have in perusal, it's right on this topic. I come at it from a little bit different direction, but it's right on this topic. And in both of these cases, I'm sticking to what you would find within the e-text. So I really think within this one, you might have to see it 2 or 3 times for it to make sense. Let me try to introduce it for us here and see what we can take away from our first pass. So first of all, as we think about, well, what makes a covalent bond? So I'm contrasting the covalent bond with like our ionic bonds. So we said before, well, we need opposite charges attracting each other. So if our electrons are negative and we have the nuclei where the protons are, we could have a combination of those that puts electron density between the 2 atoms and causes them to stick together. And when we looked with this symbolism in chapter 8, we were drawing this symbolism for an electron just as a dot. And we were thinking in this representation is what some people call Venn diagrams, was how we could have the electron density being found between both of the atoms. Now, when I'm thinking about the symbolism here, what does it mean to have this H with a dot next to it, or the 2 dots in between? This is, I think, a little bit more broadly, this was saying that this was an atom with 1 valence electron. And this dot, these 2 dots here were placing the electron density between the 2 nuclei. The reason I'm trying to think about that as 1 valence electron and think about it a little bit in those terms is think back to what we did in chapter 6. In chapter 6, we looked not at an electron just being a dot. We had a really rich description. We did a lot with thinking about where are the electrons found. Were they being found in representations like a sphere? What about this radio probability distribution where we are looking and thinking inside that sphere what was going on? We put our electrons in atomic orbitals. We did not say the electron is a dot on the side of this letter. We thought a lot about what atomic orbitals are. And that's what we're going to do now. In the chapter 9, in that second half right here, we're going to look at 2 different ways to describe bonding. And what they both have in common is we are putting the electrons back in atomic orbitals. We're not saying they're just like some dot to be shared. We're going to have to now think about what do we know about atomic orbitals in chapter 6 and come up with a description of bonding that uses that information. So let's think a little bit about what our plan is going to be and how this works. So if we think back to chapter 6, we said that an electron, well, it was in an atomic orbital and it had 4 quantum numbers. We said that the quantum numbers, they couldn't be the same for another electron in that atom. That was our Pauli exclusion principle. That's what we began to think of when we were thinking about electrons with atomic orbitals. We also saw that the atomic orbitals, they were pointed in different directions. An s orbital was spherical. When it came to our p orbitals, we had 3 different orientations for those. They could be pointed along the x, y, and z. So the atomic orbitals, they could hold our electrons. The 4 quantum numbers, they couldn't all be the same. And they were in different orientations. Let's see how this now can support our pictures of models, our model for bonding. So I'm going to do a couple things here. I'm going to add to this a little bit. This would be an orbital diagram I might have for nitrogen's valence electrons. Nitrogen is 1s2, 2s2, 2p3. This is how I might draw it. I'm not showing the 1s2. The valence electrons for nitrogen, I could draw it this way. I think this is consistent with Hund's rule. I put the electrons in independently, pointed in the same direction before I started pairing them up. Now, what if I were to draw it this way? What if I took one of the electrons, I just flipped it over? I changed its spin. Instead of being spin up, it's spin down. Hund's rule doesn't like this, but this is not a big deal. It takes hardly any more energy to take one of the electrons and have it flipped in the other direction. It's no longer the ground state. It's no longer ground state, meaning the lowest in energy, but that's not a big deal. It's really easy energetically to have one of the electrons flip it over. And in fact, at room temperature, there's enough energy that they're flipping back and forth all the time. So one thing that I want to establish is as we begin to think about our orbital diagrams, one thing that can happen we're going to see is the spin of the electron can flip over. How about for carbon? So for carbon, I show its valence electrons here. Carbon is 1s2, 2s2, 2p2. I'm going to do something a little bit different within this one. What if I drew carbon like this? I'm taking its valence electrons, and I'm taking one of the electrons, instead of having it in the 2s, I put it up here in the 2p. Now you might say, well, wait a minute, Clark, that's crazy. What are you doing there? I think that this is no longer the ground state. I think this is a little bit higher in energy than that atom of carbon all by itself. But we've seen examples where we have things that end up higher in energy initially, but then the overall energy is more stable, lower potential energy after bonds form. And when I say we've seen that before, that was exactly what the Born-Haber cycle was describing. It was telling us we can't just look at the energy that it takes to get the cation, the anion, because if we stop our story right there, it's a lot more high in potential energy than where we started. And we explained that and said, that's not that big a deal though, because when we have the coming together of forming all of these ionic bonds throughout the extended lattice, that's what made it exothermic and lower in potential energy. I'm trying to think about the same kind of thing can happen now when I'm looking at bonding in these more covalent molecules. I might have instances where I have to adjust the energy just a little bit of the atom itself, but then after the bonds are formed, those are in a lower energy than where I started. Trying to set us up for understanding valence bond theory this way. So let me now step through and sort of show you what I'm after. So let's say I have a hydrogen atom and another hydrogen atom coming together to form this covalent bond. I'm showing one of them as an electron in a 1s orbital pointed in one direction, its spin, and the other one pointed in the other direction. I'm saying that when these two atomic orbitals come together, they can overlap and form a covalent bond. Overlap, form a covalent bond. This is the same kind of picture that we saw before. I used this one when we were in chapter 8. We could initially have the atoms be farther apart, closer to a potential energy of 0. As they're coming together, the overlaps increasing between the two of them. We move to a lower potential energy, and this would be the distance where a bond forms. The way valence bond theory would describe this, it would say that for this single bond to form, what happened? We had two electrons that had different spin. One was spin up, one was spin down. And they were found in the region between the two atoms. In order for this to happen, we needed unpaired electrons. The reason they couldn't be paired up, well, we need one to be spin up and one to be spin down. Pauli's exclusion principle It works when we're talking about the atom all by itself and its electrons. It also works when we're talking about the electrons in a molecule. We can't have any two electrons within that molecule have all of its 4 quantum numbers, in a sense, be identical. So that's why when we brought it together, we needed one to be spin up and one to be spin down. Now, in addition to having one spin up and one spin down, we needed the atomic orbitals to have the right orientation, the right shape, so they could line up with each other. Now, it's pretty easy when I have a 1s with another 1s to see how one sphere can overlap with another sphere. But let's see what happens when we begin to not just have a 1s with another 1s. What if we were bringing together a chlorine atom with another chlorine atom? I show the electrons that it has there. When I'm thinking about the valence electrons, they're in the 3p orbitals. They each have one unpaired electron. Those could come together now and put electron density between the two nuclei. And when I say come together, what do p orbitals look like? Well, p orbitals, one could be along the x-axis, one along the y, and one along the z. If I'm bringing together these atomic orbitals and I want them to overlap, I'm going to bring them so they come together along that axis that's pointed in the same direction. Given this notation, it would be two of these px ones coming together so that now I can have overlap in that region. The reason I'm saying I need overlap within that region, electrons aren't just dots like next to the Cl atom. The electrons are found in atomic orbitals. So I'm thinking about, well, what is the orientation of those atomic orbitals that I want to bring together? For this single bond to form, what happened? Same story. I had two electrons with different spin in the same region between the bonds. One was spin up, one was spin down. I needed unpaired electrons to make this happen. And I needed the atomic orbitals to line up and overlap to put the electrons in this region between the two nuclei. Now, we might ask, why does the Lewis symbol work? Why does it provide useful information? Because it does, right? It's helpful to describe the bonding. Lewis's model, it doesn't have anything in his picture about atomic orbitals, but it still seems to work somehow. Lewis, he was proposing an atomic model about the same time as Bohr. He didn't know about atomic orbitals, but his pattern of placing these dots, it seems to be consistent with the orbital diagram for valence electrons, at least for hydrogen and chlorine. Look at chlorine right here. This is how our Lewis symbol would be. And this would be the valence electrons. Paired up, paired up, paired up, unpaired. Paired up, paired up, paired up, unpaired. So this little sketch that he drew, the reason it works is because it's actually consistent with this more advanced model with the orbital diagram. So it's sort of cool within that. What would happen if we're bringing together and we're forming the bond in HCl? I could draw a Lewis structure for it, but how would I begin using this idea of orbital overlap to describe what's going on? I could bring together the hydrogen atom with its electron in the 1s and bring together the chlorine atom with its unpaired electron in the 3p. Let me bring it together so they're aligned and it's putting electron density in between the two. That's how I would explain this one. For this single bond to form, notice what I had to do in order to have the shapes overlap. I had to bring together the s orbital, and I brought it together with a p orbital that was pointed in the same direction. This idea of thinking about the atomic orbitals and how they're oriented in space, that's going to be a common theme that we're going to use for the bonding for the rest of this chapter. We're thinking about those spatial descriptions. So this idea right here of trying to think about how the atomic orbitals can overlap and lead to the formation of a bond. I want you to mentally think about that for a second. Could you begin to explain the bonding in F2 using that approach? How about the bonding in HF? I'm going to share my work here in just a second, but I want you to try to think about what I was just explaining. Could you think of doing the same kind of thing in F2 and the same kind of thing in HF? Think back to what I just had in the last couple of slides, and then we'll share some ideas. Now, before I share my work on this one, what do you think? Based on the example that I just shared, do you think you're going to have a decent chance to be able to explain the bonding in F2 and HF this way?
Dr. Clark, can I ask a question about the orbitals being on the same like plane?
Mhm.
So when you have an s and a p orbital that are like hybridized, couldn't the s be on any plane since the s isn't really on one?
Yep. So I answer that two ways. I'd say that correct. I think that with the S, I don't have any spatial orientation for it. It's just a sphere. So that's never going to give me any trouble as far as saying, is it lined up the correct way? For the p orbitals, though, I'm seeing that I'm going to have to begin to think a little bit more deeply and consider their particular alignment. Now, right now, when I'm looking at how those fit together, I'm not using the word hybridized yet. You're about 5 minutes in front of me. Let's see how that applies next, though.
Okay, thank you.
So within this one, how do we begin to apply it? We're mainly in like a 3 and 4 zone. Let me show you what I would be thinking feature-wise here. So when I'm thinking F2, these would be different components I'd have. This is my Lewis structure for F2. I'm now thinking of these not just as dots. I'm beginning to think, well, what would be going on with the valence electrons? So I'm thinking that I need to be having an unpaired electron in a 2p orbital, combining with an unpaired electron in another 2p orbital. If one is spin up, one is spin down, they can overlap and be in the correct orientation. That would put electron density between the two nuclei and form the bond. How about with HF? This would be a case of combining an electron in a 1s with an electron in the 2p. One would be spin up, one would be spin down. That would be able to overlap and put electron density between the two nuclei. Which one is spin up and spin down doesn't matter. I just know I need to have one spin up and one spin down. Now, let me begin to add some ideas to our picture. How about the bonding in N2? So first of all, the very top right there, I show that the Lewis structure would predict a triple bond between them. How do we begin to think about the overlap of the atomic orbitals to produce this? So on the left-hand side here, this would be one of the nitrogen atoms' valence electrons. 2s2, 2p3. The other nitrogen, 2s2, 2p3, I've shown all of those electrons pointed down, all of these electrons pointed up, because I want to make it so that they can all pair up. Now, when I'm thinking about how they can pair up and form these bonds, now the orientation becomes relevant. One combination I could make would be where they come pointed at each other on both of the atoms, and they're coming together to give me overlap in between. This is forming what I'm going to call a sigma bond. Sigma, and then given our symbol there, sigma. It's not called sigma sigma. That's the name for that character. If I bring these together, the electron density is going to be along the internuclear axes. This axis, this line that is straight between the two of them. We're going to be using this idea. A sigma bond is one that has electron density along the internuclear axes. I've got two other ways I can bring the p orbitals together. I could bring them together where I have electron density in the p orbital above and below. When those come together to form a bond, they will not be putting electron density along this internuclear axis. Instead, it would be above and below. If you have a bond forms where the electron density is not along the internuclear axis, but rather off of it, that's called a pi bond. And I see I've got two different ways I could do that. I could have it where the electron density forms above and below, or with the other combination where it forms front to back. These would be both examples of a pi bond being formed. Electron density is again being found between the atoms, but it is no longer being found along the internuclear axis. This would be another representation for that. Another representation where we could form a sigma bond where the electron density is along the axis, a pi bond where it's formed off of that internuclear axis. This would be my description then for what takes place when I have a single bond, a double bond, or a triple bond. Within a single bond, that would be formed with a sigma bond along the internuclear axis. A double bond, the first one that I formed would be a sigma, and the second one would be a pi. And the third one would be a sigma, and the other two would be a pi bonds. So I'm adding this designation, sigma and pi, to our previous pictures where we had them as single bonds, double bonds, and triple bonds. Take a second. Let me know if you have questions on this part.
Is the internuclear axis the x-axis?
You don't have to put a designation on it. And the reason I say that, there's sort of different conventions. Sometimes I've seen it where you set it up, you call that the z-axis. In the pictures that I was just showing, the ones orbitals that I used, I think it was the x-axis. I don't think about it as having a particular label. I'm thinking that I can have one arrangement where it's pointed along that axis and two different arrangements where it's off of the axis. The question, why is something a pi versus a sigma? It comes back down to the available axis, the available atomic orbitals that we have. Meaning I can't make 3 sigma bonds because I only have one arrangement of the p orbitals that overlap that have that designation. It comes back to what are the orientations of the atomic orbitals that I'm using in order to construct those particular the resulting bonding orbitals that I have when I have the atomic orbitals overlap. Question, why can't the atom just rotate? Well, as soon as you did that, wouldn't you be changing how they're rotating? So then if you rotate something into the correct orientation, you're rotating something else out of it. This idea here, though, I'm gonna add another feature to this, okay? And at this point, when I'm adding another feature, you might be thinking, oh, man, I'm barely making sense of what you were just talking about. This is my point. You're gonna have to see this idea probably 2 or 3 times. I'll do my best to explain it within this. I got another video where I'll bring it up again, but I'm gonna add another feature to this. I'm gonna add another feature to this valence bond theory. So what if we try to explain the bonding in this? C2H4. And when I say, how would we use valence bond theory? Valence bond theory is what we're using right now, this approach of looking at the overlap of atomic orbitals. What I'd want to be able to use that theory to explain is what I see here in the Lewis structure. I think the carbon atom has a bond to hydrogen, and a double bond to the other carbon. I also think that this is a trigonal planar geometry. The angle is about 120, 120, 120, maybe a little bit smaller here because the double bond's taking up more space. I'm thinking about what do I know from VSEPR theory and describing what this molecule would be like. I want to use valence bond theory to explain this. That's what a scientific theory does. A scientific theory explains observations that you have. The observations that I have is this particular geometry. I want to see how does this theory explain this. So I really need you to pay attention with this next part, okay? When we're using valence bond theory, what did I say we need in order to have a bond form? We needed unpaired electrons, and we needed the atomic orbitals in the right orientation in order to line up and overlap. Those were our conditions, and it was working pretty well. It worked for H2, it worked for Cl2, it worked for HCl, it worked for HF, it worked for F2. It even worked for something like N2 that had a triple bond. All of those were examples where that approach worked. But we're going to have to change it a little bit in order to do this. The reason I say we're going to have to change it a little bit, this right here, this would be the valence bond, the valence electrons for carbon. If I look at this right here, and these would be s orbitals and p orbitals, I'm really going to struggle to see how this can lead to a double bond, a single bond, and a single bond. The reason I'm going to struggle with that, I only see 2 unpaired electrons. How can I explain all these bonds if I only have 2 unpaired electrons on the carbon? So the first thing I'm going to do is I'm going to look at this arrangement that's a little higher in energy. I'm going to take one of the electrons for carbon, and I'm going to promote it and put it into this 2p level instead. I said before that this is a higher in energy, but if overall it ends up being more stable, lower in potential energy, it's going to be all right. So the first thing I'm going to do is I'm going to shift it up. And this begins to get closer to our Lewis symbol. Remember, in our Lewis symbol for carbon, we had 4 unpaired electrons. We didn't have 2 paired up and then 1 and 1. We had 4 unpaired electrons. This is how a valence bond theory is getting us to that same description. So one thing that I want to keep in mind, and this will often happen with valence bond theory, I might see a changing of what the electron configuration is. Second thing I'm going to have to do is these atomic orbitals for carbon, they would not explain this geometry. When I say they would not explain it, I need to be able to explain bond angles of around 120 degrees. These orbitals are not 120 degrees. They're 90, the p orbitals are 90 degrees from each other. These angles within the molecule, all our VSEPR1, we had tetrahedral at 109.5. We had a trigonal planar around 120. I can't see how these work right here. So we're going to have to change these. Valence bond theory now is going to be changing the atomic orbitals. This is how it changes them. The atomic orbitals are going to become hybridized. They're going to be combined to form new orbitals. The new orbitals that we form are going to explain the electron domain geometry. So that's an important part of our feature for what we're doing. We are going to be making hybridized orbitals to match whatever electron geometry we're seeking to match. If we combine an s orbital with a p orbital, it's going to make 2 what are called sp hybridized orbitals. One's pointed to the left, one's pointed to the right. This notation, sp hybrid orbitals, says I've combined an s orbital and a p orbital. And I've made something that can now explain and be used for 2 electron domains. One pointed on one side, one pointed on the other. If I combine an s orbital with a p orbital and another p orbital, I started with 3 atomic orbitals, and now I'm making 3 hybridized orbitals. The notation for those is sp2. Notice it's telling me what I used in order to construct them. An s orbital, a p orbital, and another p orbital. We call that sp2 hybridized orbitals. These would explain when I have a trigonal planar electron domain. What if I have to explain a tetrahedral? I would mathematically combine an S with a P, and another P. That will now make 4 new hybridized orbitals. I started with 4 atomic. I end up with 4 that are now hybridized. What I find within this, they are pointed all 109.5 from each other. These would be called sp3 hybrid orbitals. They're being constructed from an s orbital, and then a p, and a p. This will be used when I have a tetrahedral electron domain. Now, this process of saying, how are they mathematically combined and how do we construct that? That's not something, I'd say clearly, that's not something that you're going to be asked to do. But what you are going to be asked to do is, let's recognize if we know what the electron domain geometry is, we know the hybridized orbitals that we would need in order to explain that. If it's a tetrahedral, I know that I need to use sp3. If it's a trigonal planar, I know that it's sp2. If it's a linear, then it's sp. So let me show you how that then works in this case. So if I look within with this carbon, my first thought is I need to be able to determine what is its electron domain geometry. I see 3 different domains. It's a trigonal planar electron domain geometry. And then I'm thinking, okay, what hybridized orbitals would explain that?
21, please.
If it's sp2, that's what I would use in order to explain the trigonal planar geometry. An S and a P and another P, those will now give me 3 hybridized atomic orbitals that are pointed and can be used to explain then the bonding that I would have at that particular carbon atom. If I take my notation here, I want to change it a little bit because after I hybridize it, I no longer have an S orbital and a P and a P and a P. I'm going to change that notation. So instead of having this orbital diagram this way, I'm going to group it a little bit differently. In order to explain that, I'm going to group it like this. I'm going to take the S and the P and the P, and I'm going to call that sp2 hybridized orbitals. Notice I had 3 of them there, SPP, and I still have 3 of them, but I'm changing this notation because this now is corresponding not to an S and an independent P and an independent P. It's instead corresponding to this trigonal planar shape. This will now be used to explain the bonding. This is what's taking place at each of the carbon atoms. And the way I use this then to explain the bonding, it would be this. I have one of these that is sp2 hybridized, and it is pointed towards the hydrogen atom. That would form a sigma bond. I have one of them that's pointed to the other hydrogen atom. That would form a sigma bond. Sigma, again, meaning along that internuclear axis. I've got another one that's hybridized. That would be pointing at the other carbon. Look at my picture here. In my sp2 hybridized, it's forming this triangle. And that's what I have at this carbon. I have this triangle. It is a trigonal planar arrangement. This could be used then to explain a sigma bond, and a sigma bond. Importantly, look what I have left over. I have a p orbital with an electron in it that is unhybridized. Its orientation now, it wouldn't be in the plane like this. It would be out of the plane. If all of these are flat in the piece of paper, the remaining p orbital would be pointed in and out of the plane, going towards you and going away. That remaining unhybridized p orbital, that's what could then form a pi bond with the other one. That's how valence bond theory is going to explain the bonding here. This picture, what I went through sort of process-wise, when I say it will always work to explain the bonding in the molecules like this. If we first say, well, what is the Lewis structure? What is now the VSEPR predicted geometry? I can now explain that with the valence bond theory. I can always then say, oh, okay, tell me about the environment that I'm seeking to have. What is the electron domain geometry? Let's see what electrons that I have now that can explain that. I know this is a very new part for you. Even if you've heard of hybridization before, you probably haven't heard where it was coming from. Let me explain one within this, an example like this one. Let's say I want to use the valence bond theory to explain the bonding in CH4. So this would be my Lewis structure. I look at that and I'm thinking, okay, what is the VSEPR predicted geometry? This is going to be a tetrahedral. It's going to be a tetrahedral. It's going to have sigma bonds between each of the carbon and hydrogen. The bond angle is about 109.5. It is 109.5. This would be carbon after I've promoted that electron to give me the unpaired electron arrangement. I know that I need to accommodate a tetrahedral electron domain geometry, because that's what this picture right here is. This is a tetrahedral. I'm thinking to myself, okay, how do I explain that with valence bond theory? In order to get to a tetrahedral, I need it to be sp3. I need to combine an S with a P, and a P, because that is what explains the sp3. That the sp3 is what explains that tetrahedral environment. So that's what I'm going to do. I'm going to take this grouping right here, and instead of saying it's an s orbital and an independent p, an independent p, and an independent p, I need to combine them to make it into a tetrahedral. And that's what I'm going to do. I'm going to simply list that, and instead of having it be a separate s and a separate set of p's, I'm going to bring it all together and I'm going to give it the notation sp3. And you might ask, well, why did you change it? How is that any different? It's very different. This is a s orbital and p orbitals that are all 90 degrees to each other. This is designating a tetrahedral arrangement. And that's exactly what I need to have. One of these electrons form a sigma bond with hydrogen, another sigma, and one more sigma. That's what I'm seeking to explain there. We could go on within the other set within here, but I think I'm going to stop at this point. I think it's already been a heavy class, got a lot that I've directed at you. So I'll tell you where we're at and where we're going to be going, okay? So what we're going to do next time, I'm going to explore this idea a little bit more with valence bond theory, and we're going to look a little bit more, how do we explain the environment if we have single bonds, double bonds, triple bonds within that set? And then we'll spend a little bit of time introducing how this compares with our very last idea, which is molecular orbital theory. I mentioned that I have a video on in perusal for class on Thursday. It's going to be discussing valence bond theory. I try to explain it really similarly to what you find within the e-text. But I'm absolutely sure, like I said, we got to see this idea probably 2 or 3 times. Okay? Do your best to be diving into it now. And hang with me, okay? We're really close to racing to the finish in the class, okay? I'll hang around if you got questions within this. Once again, I really appreciate your attention.
There's one question I have. If you have an octahedral atom and bonds, and you have two different atoms connected to it, how would you tell if it's
So
polar?
let me think. So if you're going back to saying, so are you saying that what is the resulting molecular shape? Is it a linear one, or what kind of molecular shape are you envisioning there?
Octahedral. The
Yeah, I would say that I would be looking at the arrangement. I could have an octahedral one where I think that I could have two different types of atoms that it's being bonded to and have them cancel. And by that, I mean, if I took an octahedral and let's say the top and bottom were atom A and the four within the plane were atom B, I think that would cancel out then, right?
Okay.
So I would be looking at the resulting symmetry for the shape that I have. That would be one where I could have a combination of 2 and 4 and it would cancel out.
But if they were 90 degrees, then it would be polar. Like instead of opposite, if
Yeah.
A was 90 degrees and
I think, yeah, in that same picture, if we're visualizing it the same way, I think if I put two of them that were in that same plane of 4 and the other 4 being the other type, I agree with you. I think that would then be a polar molecule.
okay. So you could list the same molecule and it could be both polar and nonpolar, just the way you structure it depending on how you want to.
Yeah, what you're describing right there, those would be different, what we call isomers. Same atoms present, same formula, but we're changing the arrangement for how they're put together. Those would be what are called structural isomers. And what you're describing there, that would be a property that could be different. And there's a lot of really cool properties that are different simply based on that arrangement. That's a big part of organic chemistry. A lot of them, they affect with polarized light differently. And in fact, there's some that we have in terms of our biochemistry where our bodies use a molecule that has one particular arrangement like that, but not the other one at all. So there's some interesting biochemistry on that too. Good question.
All right, that's it. Thanks.
For example, CH4, are the hybridized sp3 orbitals, those are still overlapping with the 1s orbitals in the hydrogen atoms, right?
Yep, I agree.
Okay.
Hey, Dr. Mark, just one question. So this might be getting ahead a bit, but I see the Lewis structure of H2O, and I was wondering if you would need to hybridize orbitals for this molecule.
Yeah, I'm going to say yes. And the way that my quickest way of saying I know I'm going to need to do that is if I think of that oxygen atom, its electron domain geometry, it's a tetrahedral. And if I think about with the initial atomic orbitals, there's no way I could get an angle of 109.5 out of those. Those are all 90 degrees to each other. So if it's a geometry that includes things that require angles that are not in the initial atomic orbitals, I'm sure I'm going to have to hybridize it.
Okay. Sorry, I have some loud roommates. I didn't catch that last part.
Sure. I'll give it to you again. So
okay.
the thought within that is, the first is, it's when I have it drawn that particular way, but I'm first thinking, okay, well, what is the actual geometry? The electron domain geometry is actually a tetrahedral. So if the electron domain geometry is a tetrahedral, my angles are what? Pretty close to like 109, 108 within that. If I think back to the original atomic orbitals on oxygen, I don't have any angles like that. The only way that I can account for the angles that I have to explain what's taking place there, I'm going to have to hybridize them. I'm going to have to hybridize them and use the corresponding sp3 hybridized orbitals, because those now get me to a tetrahedral.
I see. Thank you. Is the video still recording the lecture?
Yeah, it is. Do you want me to stop it or keep it going?
Okay. I just figured I could go back later to, try to solidify that. idea.
Yeah. I think that's not a bad resource. I also think I'm trying to tell the same story that you'll find in the e-text, and in my other video, I tell the same story, but in a little different way. So I think you're in a really good space to try to just bring those ideas together.
Thank you. And you mentioned that this is a theory.
Mhm.
So has this valence bond theory actually been documented? Like, do we have the capability to see hybridized orbitals?
Really good question. This is the main approach, a very powerful approach that's used to explain the bonding in much of organic chemistry, because organic chemistry is doing a lot with carbon, nitrogen, oxygen. So the kinds of bonds and environments that you have, that is what this theory does a really good job of explaining. But you make a good point, which is at the end of the day, we are using a bonding theory to explain the structures that we find in nature. We're using the theory to explain things like, oh, what kind of bond angles does it lead to? What kind of bond distances does it lead? Does it make it a polar molecule or not? So for any of these, a model is really just our way of trying to make sense of different properties that matter has. And so I would say our Lewis structure, that's a really simple model, but it does a lot of good. It has a lot of predictive power. We're making now a more complex one with valence bond theory, and it's going to allow us to predict a few more things. Our very last one that we get to in this section, molecular orbital theory, in many ways, if you were to ask me which one's the best, that is the best. That's the most far-reaching, but it's also the most complex. It will allow us to predict things and think about things differently than in the other ones. But a lot of times, the more complexity of the model, the more complexity of the theory, it gets more powerful, but it gets more cumbersome too.
Gotcha. I appreciate the detailed answer.
Sure.
Could you go back to the slide with N2 for the